What you're hearing right now is a simple sine wave. This is what it looks like as a waveform, and the frequency analyzer shows just one spike, one single frequency. That's why sine waves sound so flat, pure, and quite honestly, also a bit boring. There's just not much going on here. So let's make this a bit more interesting by adding another sine on top. The new sine pops up in the analyzer and the sound changes dramatically. Also notice how the waveform transforms. Let's keep watching these changes as we continue stacking more sines together. Each time we add another sine, the waveform gets sharper and more complex. Simultaneously in the analyzer, the spectrum starts to fill up, each sine adding one spike to the mix. The sound becomes harsher, brighter and more alive, and eventually we end up here. A sawtooth wave. If you add some effects and play something with it, we get one of the most iconic synthesizer sounds in history. And we just created it out of thin air. That kind of black magic is called additive synthesis, a process that allows you to build complex sounds by stacking sine waves together. And hidden in that simple idea is one of the most fascinating truths about sound. Every sound, literally every sound, can be broken down into sine waves. That's at the very core of how audio signals are structured, and pretty much everything you'll ever learn about audio builds on that foundation. That's why we're exploring signals today, how they work, what they look like, but also what to look out for when you're working with them. So let's jump right in and make sense of all of this. As a start, it's probably best to get some definitions out of the way, just so we can be sure I don't use any terms you haven't heard before. So first, what is a signal? In audio, every sound is a signal. Whether it's instruments, voices, or random everyday noises, it doesn't matter. If it's a sound, it's a signal. And there are two main ways we can look at a signal. We can look at it in the so-called time domain or in the frequency domain. The time domain representation of a signal is its waveform. So how the signal's value changes over time, its ups and downs, moment by moment. The frequency domain representation of a signal is its spectrum. In other words, what frequencies are present in the signal and at what levels, at any given moment. The last term we should introduce right away is the complex signal. A signal is called complex when it consists of more than one sine wave. So our intro sawtooth was in fact the complex signal. On top of that, there are two categories we can group complex signals into: harmonic signals and inharmonic signals. But to be able to understand the difference, we first need to take a closer look at our building blocks, sine waves. When we look at our sine waves waveform in the time domain, a few things stand out right away. It's extremely smooth and it's periodic. Periodic means there's a pattern that keeps repeating over and over again. The highlighted section is called a cycle, or one oscillation of the wave. Once the cycle is complete, the exact same pattern starts again and keeps going forever. Frequency tells us how many of these cycles happen every second, and it's measured in hertz. So if our sine wave plays at 220 Hz, that means it completes 220 cycles per second. If we increase the frequency, the pitch rises and the wave cycles faster. And if we decrease the frequency, the pitch lowers and the wave gets stretched out. The wave's amplitude describes how far the waveform swings up and down. The higher the amplitude, the bigger the swings and the louder the sound. If you lower the amplitude, the quieter it gets. Now if we switch over to the frequency domain, we can see how all this connects. Here, our sine wave shows up as a single spike at 220 Hz. And that's an important fact, because a frequency you're seeing in the analyzer is a sine wave. When you raise the frequency of the sine, that spike moves higher. When you lower the amplitude, the height of that spike shrinks. So the time domain and the frequency domain are really just two different ways of looking at the very same signal. And now let's put all of this into context by bringing our sawtooth wave back in as a comparison. Obviously, the sound is completely different, and this is reflected by the sawtooth having many frequencies in its spectrum. But notice something interesting. They have one thing in common. Both the sine wave and the sawtooth share the same base frequency. this case, both have a spike sitting right at 220 Hz. If we switch our focus back to the time domain, it becomes clear why. Both waveforms have a repeating pattern that cycles at the same speed. The shapes of oscillation may look completely different, but they complete one full cycle exactly in the same amount of time. In this case, it would be 220 cycles per second, and that's where both waves share the same base frequency of 220 Hz. In musical terms, we would say they're playing the same note. And this is the perfect moment to define what a harmonic signal is. When we look at a complex signal in the frequency domain, each frequency component we see is called a harmonic. The lowest of these frequencies, or the first harmonic, is the so-called fundamental. What makes the Sawtooth wave a harmonic signal is the precise mathematical relationship between its harmonics. Each harmonic sits at a whole number multiple of the fundamental. So again, in our case, the fundamental is 220 Hz. Therefore, the second harmonic sits at 220 Hz times 2, that's 440 Hz. And we just keep increasing the multiplier per harmonic. So 220 Hz times 3, times 4, 5, 6, and so on. And this relationship is fixed. If you transpose the saw up or down, the entire set of harmonics shifts with it, and the relative spacing between them stays exactly the same. The second harmonic, for example, will always be double the fundamental frequency. And every harmonic signal has its own unique mix of harmonics. That's what makes a guitar sound different from a piano, even when they play the same note. No matter what that harmonic mix looks like, as long as all the frequencies are whole number multiples of the fundamental, it's a harmonic signal, and our ears perceive it as tonal and musical. And it's this precise mathematical relationship that separates harmonic from inharmonic signals. Because inharmonic signals are also complex signals, but the key difference is that the individual frequencies aren't whole number multiples of any fundamental. Think of stuff like white noise, drum cymbals, or just everyday sounds around you. All of those are made up of countless sine waves, but they're not organized in any neat harmonic pattern. When we look at their waveforms, we see complete chaos. There's no repeating pattern, no cycle that comes back around. And that's why these sounds don't have a clear pitch. The spectrums reflect that same randomness. Instead of clean, evenly spaced spikes like in our Sawtooth, we see sine components scattered all over the place. Of course, even within that randomness, there's still character. White noise doesn't sound like a crash cymbal, and both sound very different from wind or a car engine. But we generally perceive these sounds as dissonant, noisy, and often unpleasant, especially compared to the ordered, musical nature of harmonic signals. And now let's bring all of this home and see what this actually means when we're working with audio. As we saw in the intro, when we went from sine wave to Sawtooth, the waveform changed from smooth to sharp, and the spectrum became fuller and richer. That's not a coincidence. In general, the softer and rounder a waveform looks, the fewer harmonics it contains. Sharp edges, on the other hand, always hint at a lot of high frequency content, so the shape of the waveform literally gives away the character of the sound. And as we said earlier, the time and frequency domains are just two ways of looking at the same signal. A change in one will always lead to a change in the other. For example, if you take our Sawtooth and filter it from the top down, removing one harmonic at a time, the waveform gradually morphs from a sharp saw back into a perfectly smooth sine again. Or imagine we cut a sine wave by editing an audio clip in a DAW. This sudden jump from 0 to full level creates a sharp edge, and in the analyzer it instantly shows up as a quick high frequency burst. Even when we're just low passing a kick drum to clean it up, we might accidentally remove the transient, because what is a sharp edge in the time domain, so transient, also shows up as a sharp burst of high frequencies in the frequency domain. So if you filter too much, you might accidentally strip away a lot of the sound's presence and punch. And there are like a million more examples, but I think you get the idea. The time domain and frequency domain are always connected. Change a signal in one and you'll change it in the other. Sometimes that's exactly what you want, other times it introduces side effects you didn't expect. Either way, it's something you should always be aware of when shaping and processing sound. Now, we're nearing the end of the video, so let's finish by talking about how signals add up. We've already seen this in action when we created our Sawtooth from scratch. But generally speaking, when you have two signals, let's just call them signal A and signal B, and you play them simultaneously or sum them in a master bus, it's a simple addition process. So for each point in time, you simply add the current value of signal A and B together to form the resulting signal C. That means in the time domain, the waveforms add up. In the frequency domain, you can think of it as merging the spectrums together. But this is where the concept of phase becomes important. Phase describes the relative timing or starting point of a periodic signal within its cycle. If two identical signals are synced in phase, their ups and downs line up perfectly, and the addition results in an amplitude twice as big. If you shift the phase of one of the signals, they start to cancel out. And when you shift them so that the peaks of one signal perfectly line up with the valleys of the other, they in fact cancel out completely, and the result is absolute silence. But phase and its problems, it's a big topic we run into over and over again as the series continues. So I think it's okay if you leave it at that for today. And if you want to dive deeper into how all this connects, stick around for the next video, where we're going to explore the difference between analog and digital signals. But that's it for today, and see you next time.